So yeah, machine learning for continuous integration. As I said, I work for Google. You can see there I've got my Twitter handle, my GitHub, and my blog for, hey, used to do blogging. Okay, so a clarification on machine learning before we get in too deep to this. I'm going to cover at the very, very end a tiny little bit of TensorFlow. Most of this talk is going to be about another thing in machine learning called k-means clustering. It really is machine learning. Proof by Wikipedia that we are talking about machine learning with this stuff. But like I said, there's not a whole lot of TensorFlow. You're not going to see any neural nets in this talk. So if that's going to be disappointing to you, you might want to consider a different talk. I won't be offended if you leave. So some background. Oh, asides. I talk very fast, but I also have lots of opinions. And I don't have enough time to go into all the things I want to talk about in this, so I will have aside slides. And if you're interested in any of those topics, grab me right after this talk out in the hallway, and I would love to talk your ear off for a couple hours about any one of those topics. So, all right, so we're going to do Skia. What is Skia? Introduction to k-means clustering. Applications of that, and some interesting bits out of that. There's also a little detour in the middle. So Skia.org is the site. It is the open source cross-platform 2D graphics library that you have never heard of. That's the website, Skia.org. Give you an idea of kind of what it does as far as drawing. You've never heard of it, but you probably use it on a daily basis. It is the 2D graphics rendering engine underneath Chrome, Android, Flutter, Xamarin, and lots of other products that we don't even know about because it's open source. Nobody has to tell us if they're using it or not. So we are used by Chrome and Android, so we have to be used on a whole slew of different platforms. Right? Windows, Linux, Mac, Android, iOS, Chrome OS. Skia itself, as a rendering library, has a whole bunch of different backends. So it is focused really on kind of smaller end machines, so it can be used on smaller devices. So Skia was originally a project that was purchased and then open sourced by Android to be the basis of the Android operating system. And has since then been adopted by other projects. So it has a bunch of backends. One is just the CPU. So we're just use the CPU to do rasterization and draw using that way. But we also have an OpenGL backend. We have a Vulkan backend, a PDF backend. We just landed, very early days, a compute backend. That is still very, very, very early days. We also have experimental XPS and SVG backends. So, of those backends, we have OpenGL and Vulkan. And that right there implies a huge amount of testing on real-world mobile devices. So my role on the Skia team, the Skia team is about 30 engineers. We work out of Chapel Hill, North Carolina. Yes, there's an engineering office for Google in North Carolina. It's always the next question. My team is the infrastructure team. So I'm responsible for testing Skia. That's testing for correctness and testing for performance. And I'm on the infrastructure team. So we build and run all the machines that do the testing, all the analysis tools that go on top of that. And so we get to our first aside. Having done a lot of testing, you do not want to know really the state of OpenGL on mobile devices, what you can and cannot count on. And just even if everything was perfect, the remarkable amount of wiggle room that exists in the OpenGL spec for what actually amounts to math. So there's a huge amount of testing to be done here. And so this is now part of my lab. So what you're seeing there is one rack in my lab. That is 128 Raspberry Pis and 128 mobile devices attached to them, Android and iOS devices. What you're looking at in there is for each of these devices, so every device has its own Raspberry Pi attached to it. That Raspberry Pi is attached to a power over Ethernet adapter, which switches out connectivity and power. That powers the Raspberry Pi powers the phone. So we're only connecting one line in, which is the Ethernet, power over Ethernet. And so we just plug in 128 of those. Down below is we have our little 3D printed cases that hold the whole thing together. So I'm not going to go any more into this, but if you want to talk about using Raspberry Pis at scale, things about how you go about cooling phones and how cool you need to keep them, and what you do about expanding batteries, which happens right before you get exploding batteries. And we could talk about things like burn boxes and all the material you need on hand for those things. Luckily, we've never had an incident, but we are prepared. Everything I'm talking about here today is open source. Okay, Skia is an open source library. Download it and build it today. My infrastructure team, everything we do is open source, right down to the 3D models for the things that we print. We also have laser cut models for other devices that we put together. So all of that is open source. And there's some other open source projects in here that have been spun out of my group also, Polito and Elements SK. So we run on all these platforms. We run on all these different configurations for all the backends. I haven't even covered a smidgen of what a lot of the other options are available in Skia. Skia can render as 8888, which is probably what you're normally used to when you render, as far as 8 bits per channel of red, blue, green, and alpha. But it can also do 565. And there's a whole bunch of configs in there. At the very highest level, we have a lot of tests. And as you can see, this is directly out of our config file as of a couple days ago. So 585 separate configs. Each line in here is what we would call a bot. So that means this is a machine sitting somewhere, either in the lab or up in the cloud, virtually is going to download and run some tests. Either it's a correctness test, and it's going to render some images, or it's going to do some performance testing and see how fast each of the individual tests run. And we get numbers out of those. To give you a sense of scale here, because we have all of these machines, all of these configs, all of these tests, every single commit that lands in Skia, we test. We render 1.5 million images for every single commit, and we generate 250,000 performance values. We land about 30 commits a day. That's a lot of data. 250,000 commits, 250,000 performance values is actually what I'm going to be kind of mostly focusing on right now. It's driven a lot of these things I'm about to talk to. If you're sitting there as an engineer, you land a change, you go, hey, did this make things faster or slower? You're not going to look through 250,000 traces, right? This is not going to work. We need to build some automation to pull out the information that we're looking for. Was this good? Was this bad? So, like I said, I have a team of 5 engineers. The 6 of us have built a slew of applications that you see here. These are 6 out of, I think the last time we counted, 60 separate web applications we built to support all of the infrastructure around Skia. Again, this leads to another aside. If you want to hear me rant, I can talk a long, long time about custom elements, HTML5, and frameworks versus a la carte web development, i.e. not using a framework to build things. But let's go back. 585 configs. Before I go on, let's back up and give you a little background on the nomenclature of kind of what we call things inside Skia, how we build stuff. So a CL. CL is a change list. Working in open source, it's equivalent to a pull, right? Pull request. Tribot. A tribot is any one of those lines in that config. So it's going to be a config that pulls down some scripts and starts running the tests on it. So each one of those, we have 585. We have lots of bots. We have 585 configs to run on those bots. A revert is just, oh, I landed something. It didn't work. I pulled it back out. So same thing you see in Git. We use Git as the backend. CQ is the commit queue. So when somebody lands a commit, we cannot run all 585 tests before we allow the commit to land. Some of those tests take a very long time, 45 minutes, 2 hours, whatever. There is a decent subset of them that can complete in about 20 minutes. And so those are the ones that we get on the commit queue, where those have to pass before the commit is actually allowed to land. And finally, the waterfall is this big view that we have of all of the data that we're now collecting. So this is available. You can actually see this yourself at status.skia.org. This is the current state and health of the library. What you're seeing on the right-hand side are the auto rollers. This is another aside. If you're working in a big open source project that's actually composed of lots of small open source projects, you're doing a lot of rolling, right? So Skia changes 30 times a day. Multiple times a day, we will roll into Chrome, which means Chrome has a dependency upon us, which is just a deps file, which just says, we are currently using Skia at this git commit hash. And then we go in and go, okay, we want to upgrade you to 3 more commits that we added today. So we update that deps file, we run a bunch of their tests on their commit queue, and hopefully that will land. And that way we keep our projects in synchronization that way. We have lots of rollers, right? So these are just a small subset. So I think we currently have somewhere between 18 and 20 different rollers that are either rolling dependencies into Skia or rolling Skia into other dependencies. We're now actually really good at rolling, so we actually now roll from other projects to other projects that have nothing to do with Skia. So that's that. Each one of these columns you're seeing on the display in that middle section represents a config. It's one of those lines in that file. Green, all right, invisible, it's actually green on my screen. See, it's green here. We obviously have a color issue. Invisible on the screen means everything is good. It's green, it's happy, that test passed. The red on my screen actually looks, yeah, orangish brown there. Those are things that were bad, where the tests failed. Purple, which actually looks like purple on there, are places where the system failed, but the test didn't fail. So we sent it out to an Android device, and then somewhere in the process, we lost communication with the Android device. So that doesn't kind of count against the Skia library. That's something on the infrastructure side we need to look at. All right. So this is kind of our view. This is one of the apps my team has built, and this is where we monitor on it. This is just what's called the interesting view. These are of the 500 plus bots that have run. These are things that are interesting, i.e. they've changed from good to bad recently. So back to landing and reverting. So you may land a CL, and then you may say here, so Robert Phillips landed a CL, and you can see where some tests failed. So Robert's on top of his game, he immediately reverted it, all right? But that means we have run all of the tests for his landing and all of the tests for his revert. Now that CL landed because those bots that failed were not on the commit queue, right? But we've now done basically 2 rounds of testing on everything, 3 million images rendered, and we haven't gotten any further. Well, we now know where that CL breaks. So this led us to our first machine learning project. Oops, where are we going? Okay. Our first machine learning project, which will be a cautionary tale because it didn't work. So hopefully you can learn from our mistakes. So the goal here was we want to try to avoid this happening, where you land a CL, find out some bots break, bots that aren't on the commit queue, and then you have to do a revert. It would be great if we could look at your change list and say, you know what, you should actually run on this bot over here. It's not on the commit queue, but you should really run it because we think you might break that one, right? So that's why we're not expanding the commit queue to everybody, to all 500 bots. We're not going to slow down the system to 2 to 4 hours per commit, but maybe we can hint to other people this is where you should be testing. So that was it. Suggest bots that engineers should try in their CLs before submitting code based on the code that was changed. So this is kind of a really, really simple mapping of here's the files that have changed of the 10, 20,000 C++ files that are in Skia, and the likelihood that you're going to break a bot. This is a little tricky though, right? Because the first thing we need to do is to get nice clean data. We need to distinguish between, we need to actually find in our history of the 20,000 commits that have happened to Skia, where this actually happened first, right? That's kind of our training set. So we need to distinguish between reverts that cause bots to go green versus broken bots versus noisy bots, right? Because there are some bots where the tests are just flaky and occasionally they show up as red, right? But there are cases where we can look at it, in this case, where we said, oh, Robert landed the CL, then he reverted it. Those, however many bots there are there, 4, 5, 6, 7, 8, 9, 10, 11, those 11 bots went back to green. So we have a good idea that all the files in that CL, they're somehow related to those machines there, because they went from green to red where we reverted that CL. But here's kind of our first problem. When you do a revert, a lot of the times, what happens is Robert may go and go, oh, okay, now I know what I did wrong. He may actually take that very same CL in Garrett, which we use for code review, tweak it a little bit, and land it again. And so the first commit had whatever its name was. The second commit said revert. The third commit may say revert, revert, because it's actually reverting the previous revert. So we built this system where we would go through and look through all the commits and look for these changes, and now look for the parity of the number of reverts in the commit message. Okay? So if there's one revert, that's a real revert. If there's 3 reverts, it's a revert. If there's 2 reverts, it's actually a land, right? So we had to count the number of reverts that go in there. So that's where we're at with there. And I think I found one CL that actually had 5 reverts in it. So things can get a little tricky. So, all right, second problem. These trybots, a lot of trybots are run in the commit queue, right? And those are pretty good standard pieces of information. There are other trybots where an engineer can be working on a CL, spin up some data, go, yeah, I'm not quite sure, and they'll run some trybots by hand. They're not actually trying to commit, but they can trigger trybots with their change in place. The issue is, that is really noisy data. We ran some analysis over it. We tried to pull out some information from it. It was garbage, right? Because a lot of the work is experimental. It's like, oh, I got this way of doing it. And then they'll try some trybots and go, oh, Windows doesn't like it when I do it that way. I'm calling a function that Windows doesn't have, or some, oh, it's, this is going to be problematic on ARM versus Intel. So there's a lot of experimentation that goes on in the CL. There's a lot of tries that the engineers will kick off that give no useful information. And so it's very noisy. So we have to ignore those. So we can only use the trybots that are on the waterfall. Then, now because we have this disparity between the two, we now have what is our second big problem. The data that would inform the trybot runs before a CL lands, but only trybots run after a CL land could be used for training. Right? So we were going to have this system where we told the engineer, oh, by the way, yeah, your code changed here, you should run this bot. And so they would run that bot ahead of time. So the waterfall would actually never see that bot succeed or fail. It would only see it succeed. So in the course of about a month, if we kept rerunning our analysis to look back over time to retrain our model would get really stupid because we're basically having our own data is in a loop there. And so the system would get dumber over about a month, and then it would start suggesting, oh, look, stuff would start breaking on the tree again. Oh, I can learn from that, and that would feed back into the system. So this caused us an issue there, where things were not going to be working out for us. The final one, this is the one that, drove me to drink, was then in Garrett, they added some smarts to it, and if it saw that you were actually relanding a revert, it would actually change and put the word reland in it, not revert. thus killing my algorithm for classifying things. And at this point, I decided, okay, that's enough. This is not going to work out. So things we learned from this process are, one, make sure you have clean data, and getting clean data can be very difficult. And two, beware of the feedback loops, because this was a system that, if we had put more time in, it would have been totally wasted, because in a month, it would have then basically worked itself out of a job. So let's take a little detour now into k-means clustering. All right, so what is k-means clustering? I'll leave all the Skia stuff behind. If you want to pull this up in your browser, you can. bit.ly k-means-OSCON. This is a web post I put together earlier this week. It is a simulator to help you simulate and get a little feeling for what k-means clustering looks like. So if we, hey, it looks green. Cool, it's not invisible. All right, let's start with a group of what are called observations. In this case, they're observations of two parameters, x and y, right? And we've got a little scatter plot here of those observations. You can look at that with your eye and go, there's 3 clusters there, right? That's very easy to do for your eye, all right? We want some math to be able to algorithmically pick out those clusters ourselves, all right? We want to do a system where, all right, we'll start with 3 clusters like this, and we would like to end up in an area where we've got, oh, look, I now have 3 clusters, and I've picked out what those 3 clusters are, kind of where they're centered. Right. So you can play with that at your desk, but this is what we want. We want to figure out where those clusters are. Right. So the way the system works is actually incredibly simple, right? You start out, and it's called k-means clustering. The k is the number of clusters you think that are there, right? So you pick k observations, and there's different algorithms for different ways. The best way, one of the easiest ways is just pick, k of your samples at random. And we're going to call those the centroids. Centroids are representatives of a cluster, right? Pick those out, and then now that you have your centroids, go through your data set and figure out what centroid each point is closest to. Right? Very simple. We're going to say, oh, I'm closest to you, I'm closest to you. Now you've got all your points, they're all categorized. Now that they're categorized, recalculate where the centroid goes. It's going to be in the center of all those points. Right? Just 2 steps. Categorize your points, recalculate the centroids. Calculate your points, recalculate your centroids. Okay? And then just do that. Okay? This will always settle to a local minimum. Important word, local. Local means sometimes wrong, but it's local. It will always get to a minimum. So we can actually walk through that here. So if you're on the simulation, you can see we can generate random sets of points. I actually spent more time working on the algorithm for generating clumpy data than I did actually implementing k-means clustering. That is neither here nor there. And you can see where we have circles now. We've started, and we've picked out 3 points at random to be our starting points. Those are the centroids. And our first step is we assign observations to those clusters. So you can now see all of the orange ones were closest to orange, all the blues were closest to that blue centroid, all the greens closest to that green centroid. Now that we've done that labeling, and they're all categorized that way, now we recalculate the centroid, right? Where is the center of each of those clusters? So now you're going to see, for example, that blue one should move down, and the orange one should probably move up. So if I click here, that's exactly what happened. Those are now the centers of those points. Now what do? Now that they've moved, we now go back and relabel everything based on what they're closest to. And you can see, we hit a huge amount of the green over there, and now we update our centroids. Now we update the centroids color, and you can see those centroids are kind of moving around the screen, and we will eventually settle into something that doesn't quite categorize it perfectly. And this is an important thing to learn. you can then, restart. So it's a fairly actually fast algorithm. And so one of the things you do when you do k-means clustering is you do a lot of it, right? Pick a bunch of random starting spots, do the k-means clustering. You're going to get a local minimum. Cool. Start again. Pick a different set. Do k-means clustering again. You may get an even better fit for the next time. All right. A little more nomenclature. When we talked about these things, I think I already talked about it. When I'm running a test, what we talk about are traces, right? Normally when you see lots of graphs of data, people talk about time series. I don't care about time. I only care about commit series. I had a commit, I had a commit, I had a commit, and I'm lining up my data with those commits. I don't care if they were 2 minutes apart or 2 days apart. It doesn't matter. That's when the code changed. That's all that matters to me. Regression. So this is what we're looking for. We're looking for regressions. Can you actually see that? Apologize. Bunch of little dots. So regressions are two things. One, they're steps either up or down, obviously, but then they're persistent. They stay that way for a while. If you're testing on phones, you're not going to have really consistent data. Okay, you're going to have things like thermal throttling, right? If your phone heats up, it'll frequency scale down to a lower scale. Guess what that does to your performance metrics? It changes them. Your phone may overheat and turn off, if it's a big core, little core system, it may turn off the big cores and shift the work to the small cores. That changes your performance. You might not know that there are both frequency scaling for both the CPU and the GPU the GPU itself may have thermal throttling separate from the CPU. These are all important and painful things we learned over the past 3 years. So this is a series of traces, right? So we're running some tests. We're running a test over these bots. We're gathering all this data. They run at different scales. If I'm running on a desktop machine with a monster GPU in it versus running on a super low-end phone, I am going to get different metrics. I'm running the same exact test, but obviously there's going to be 1 to 2 orders of magnitude possibly between the performance times I'm getting out of those tests. And so it makes it hard to compare. So if I showed you a graph of this and I said, how am I doing? You'd probably say, hey, that looks pretty good, right? But the problem is you're going from things that are 1 millisecond to complete up to things that are 35 milliseconds to complete, and it's hard to detect that. So we're going to do something called normalization. Right? Because I don't really care about the relative scales between the data. I just care if something changed, right? I don't care if the performance test is actually accurate to what you're going to get on your phone. I don't care if it corresponds to a frame rate or whatever. I'm concerned about actually saying something changed, and then somebody needs to look at it, okay? So I'm going to take all this data and normalize it. Normalize it to a mean of 0, so you just take the mean and subtract it, and then normalize it to a standard deviation of 1. So it's all consistent. That's the same exact data. That's the same exact data normalized. Now you look at that and go, oh, what changed? Now we need to get an engineer. Whoever made that change, that CL, will go over and go tap, tap, tap. Can we look at this? So that's the importance of normalization, is we take the time, we make it time invariant, right? We're going to scale it down and get it to the point where we care about the shape. All we care about is the shape. So think about this. Let's back up a little bit. This is just the last 2 points of that trace, right? The last 2 points. We already had a little experiment we did with 2 points, which was that clustering, right? If I could say 1 point was the x and 1 point was the y, I could actually map it into that 2D grid, right? So if I just had a trace with 2 points, I could map the 2 points into the x and y's. That gives me a point in the grid. And now here's the trick. Things that cluster together, if they're normalized, are going to have the same shape, right? If the x's and y's, if the 2 points are pretty close to each other on that normalized graph, if they both go up, like if they're tilted, one's low, one's high, and they're both low and high, that's going to map to approximately a similar position in that xy coordinate space. So things that look the same are close. So let's expand that now. Instead of looking at the last 2 points, let's look at the last 3 points. You'll be disappointed that I did not put together a clustering graph for 3 dimensions, but I'm just going to jump straight to this space, okay? Our normalized traces are just points in n space, in an n-dimensional vector space, where points that are close together are similarly shaped, right? That's all we're getting to, is points are similarly shaped. The k-means clustering stuff I showed you before, I showed it to you in 2 dimensions. K-means clustering doesn't care how many dimensions there are. It wants to know what the metric is about how things are far apart, and then it labels them. It doesn't matter how many dimensions we have. We have 27 dimensions like we have here. K-means clustering still works. So we have now taken our data, put it into a space where the shapes are similar, and now we're going to use k-means clustering to cluster them, to find similarly shaped buckets of traces. Once we have that similarly shaped bucket, right, we will end up with the centroid, right? The centroid, which is that awesome invisible line over the graph that you're looking at now, is the one line that kind of represents that bucket, represents everything that shows up in that cluster. Now, instead of actually dealing with the 50 or 300 traces that are there, I can just look at that one. And now I want to look at that one centroid, that one representative of the cluster, and go, does this look like a step function? Does it look like a regression? So we want to say, does it look like a regression? So a little hand wavy here. So we have this idea of R. R is our regression factor. And we're going to look at 2 things here. We're going to look at the sum square of error between what those bars are and then the step. So remember, the centroid is already normalized, right? We're going to take the left half and the right half, and we're going to take the averages of those. That's what those bars represent. So those are the averages. And now I'm going to look at the difference between those 2 averages. If one's higher than another, I probably have a step, right? But now I'm also going to look at the sum squared error between those dots on the right-hand side and the left-hand side, and what the actual average is, okay? So another way to look at it, if you're used to looking at things in signal processing terms, right? Taking the average of all those points on the left-hand side is just a really, really, really low pass filter, right? We're just taking a low pass filter and we're taking all the noise out of it. That's what the mean does. The sum square error then is kind of a measure of how much noise we took out. Those are the 2 things we're looking at. What's a low pass filter on that left-hand side, and then how much noise did we end up removing from the system when we did that? Then we calculate R, our regression factor from there, which is the step size, the difference between those 2 means, how much did it move, divided by the sum squared of errors, right? How much is that noise factor? And you'll see this gives us a number that can be correlated to how much it looks like a step function, right? Because if the step gets larger, right, it's step over SSE. If step gets larger, R gets larger. If the SSE gets smaller, right, the error, if there's less noise that we've taken out of the system, if that gets smaller, we're dividing by it, therefore R gets bigger, right? And the other ways around. So this R is now a good measure of how much that centroid looks like a step function. So this is our algorithm. This is how we do this. We take all of those traces, we normalize to a mean of 0, standard deviation of 1. We cluster all those normalized traces. Then we throw out most of that data and just look at the centroids. We calculate R, the regression factor, for each centroid. And if that regression factor, the absolute value, is over some threshold, then we'll trigger an alert. Now, some threshold is because 2 things. 1, absolute value of R, because we don't care if it's a step up or a step down, right? If performance got worse, we care about that because we may have slowed something down. If it got faster, A, it's always good to know we made stuff faster, or B, we really want to detect, did it actually go to 0, right? Did we actually stop running the test, which has happened? So detecting down is also good. And then Like I said, repeat. Remember, k-means clustering isn't always going to give you a great answer. So do this continuously. Continuously grab your data, continuously cluster, look for it. 1 out of 10, 1 out of 100 times when you cluster, you may find something that's worthy of an alert. So, other parameters to tune that happen in here. 1 is k, how many buckets are you going to use? And 2 is the radius, right? So when I showed you this, we were looking at 1 commit that was a bad commit. We picked so many commits to either side of that. That's the radius. That's an important tuning parameter here. If I pick a k radius that's too large, right? I'm looking too far out in time, and other CLs may have come along that actually changed the performance, and then I'm not going to look like a step function anymore, and I may miss it. On the other hand, if I pick the radius too small, I'm too prone to noise. So you have to balance that between those. And that is really just heuristically, you're just going to do a bunch of this work, find things that look like clusters, you know, eyeball them, find a number, and use that. So noise, radius, some threshold. So this is one of the apps that we have actually built, perf.skia.org. You can actually go and see this sort of analysis. So we have the ability to go, all right, I'm interested in this commit, pull out the data, do the clustering, and you can see the information we have now presented here. So this first thing that clustered is actually a regression. You can see up there it says the regression factor is negative 51.4. So for our data sets, we found 50, at least the way this is configured now. 50 is a good R value to trigger a regression. We have other data sets for other teams. They trigger on 20, they trigger on 100. Totally depends. But once you get it settled in, it usually works pretty well. The cluster size. So 808 traces out of the 250,000 traces that we run fall into that bucket and look all the same. There's our least square error and our step size. And then you can actually just start going through and triaging these things, looking at how they work. So what if you don't actually have performance data that you're measuring, right? What if you're just doing regular old continuous integration? You're just building, you're just compiling stuff. All the stuff I'm talking about is irrelevant to you. Not really, okay? Because we also feed into our system how long each bot takes to run the tests, whether it's doing, or the compiles, or whatever. This is an alert we got triggered off our compile time. Nothing with the performance metrics we were taking. We just saw this tripling, quadrupling, quintupling of the speed it took on Windows to compile. And this is what happens when an update comes through and Windows Defender gets turned on and starts protecting your work directory. This tends to slow down the compiler and the whole system. So it isn't just a useful system for just performance metrics of the type I've been talking about. Think about all the other metrics that you have available that your CI system is generating. How long does it take? How long did it take a CI job to get scheduled? How long did it take to finish? How long to upload the data after the fact? All of those are very interesting metrics that you probably would like to know if they changed. And if you have a huge CI system, probably way too many graphs to inspect by hand. And so this is a useful system for that. I said there's very little bit of TensorFlow in here at the very end because the math I've talked about is basically pretty trivial, okay? It's a module in TensorFlow. There's a k-means clustering thing in TensorFlow. And the example code on that page that describes that object, the k-means clustering object, is a good one for what we've been talking about. You can see there the number of points. You can see the number of dimensions, right? They start with 2, just like we did when I did the clustering at the beginning. That was a 2-dimensional graph that we did the clustering on. Later, the dimensions go up, on some of these to 15, 17, 27, whatever of how big you decided to take your traces and cluster over. Again, the k-means clustering algorithm, it doesn't care. It doesn't care about the dimensions. And then it goes through here, it does the clustering, and then you get your outputs on that. And again, run those repeatedly. So, interesting things here. K-means clustering. interesting way of pulling data out of these systems. We talked about traces in the commit series, and like I said, these apply not only to the performance test results, but to any sort of data you're getting out of your CI system. This is a good way to pull data out of there. So, all right, thank you. And like I said, for any of those asides I had out there, please feel free to grab me in the hallway, and I'd love to cheer your ear off about any of them. Thank you.